Design Part 2. I'm Lisa Marflack with the Transportation Research Board. Before we get started with the presentations today, let's first review the credits that TRB is providing, as well as demonstrate how the audience can communicate with TRB during the webinar. TRB will provide 2 professional development hours to professional engineers that attend the entire webinar session. And as far as today's learning objectives, at the end of the webinar for the systems Rodel and Arcady, participants will be able to discuss the background and basis of these software, explain the critical inputs, describe the step-by-step data input, discuss output, analyze output, and discuss specific use cases for Rodel and Arcady. For instructions on retrieving your certificates, please review the reminder email that you received this morning or the follow-up email that you'll receive after the webinar for instructions. And just a reminder that for PDH credits, you must register and attend the webinar as an individual. For groups, only the person who registers and attends the session is eligible to receive a certificate. TRB will report your hours within 1 week of the webinar, and please feel free to contact Reggie Gillen with any questions about receiving PDHs. The American Institute of Certified Planners has approved this webinar for 2 certification maintenance credits. Report your CM credits at planning.org/CM. Attendees are automatically muted when they join the webinar. However, they may ask questions by using the GoToWebinar control panel, which appears on the right-hand side of the screen. The questions that you type in are not visible to other attendees. Instead, they're sent directly to TRB and the moderator. Please type in your questions about using the software or questions about the panelists' presentations here, and we encourage you to type in your questions anytime throughout the broadcast. After both presentations, the moderator will read the questions that he has received out loud. And if you don't see your control panel, it may be minimized on the right-hand side of the screen, so go ahead and click on that red and white arrow button to access the control panel. Attendees often ask how you can receive a copy of the slides. Please review the reminder email that you received this morning, which includes a link to the presenter slides. And we also pasted this link into your control panel, so you'll see the link there. After the webinar, you'll also receive this link along with the link to the recording of today's session. So at this time, I'd like to go ahead and introduce today's panelists and moderator. Today we have Mark Johnson. He's the owner of MTJ Roundabout Engineering. James Bedingfeld is a senior traffic engineer at Transportation Research Lab. And Brian Walsh is the State Traffic Design and Operation Engineer at Washington State Department of Transportation. Brian will be introducing today's presentations, and he will be moderating questions from the audience at the end of the webinar. So at this point, why don't I go ahead and ask Brian to provide his introductory remarks at this time.
Thank you, Lisa. Good afternoon for some of you, and good morning to the rest of you. As Lisa noted, my name is Brian Walsh. I'll be moderating today's series. This is the second in a series of tools and analysis for roundabout design. We're going to hear specifically about the 2 programs, Rodel and Arcady, which have a strong design element. And both presenters will do a very good job of this since they work with these models on a daily basis. I want to put a plug in for the TRB Roundabout Committee. I'm a co-chair of that committee along with Gene Russell from Kansas State University. And Gene has been a big player in getting a lot of these webinars about roundabouts onto the web here so that the attendees, you people, can enjoy them and learn from them and hopefully apply them and implement roundabouts. At this time, I want to go ahead and get it started and not spend a lot more time on the opening introduction. And our first presenter is going to be Mark Johnson. He will be talking about Rodel.
All right, great. Thanks, Brian. I'm now passing things over to Mark to administer his presentation. So Mark, when you're ready, you may accept the screen control and begin your remarks. Great, we see your slides.
Thank you.
Thank you. And just a reminder to launch your slides in full screen mode. Perfect. Thank you.
Very good. Well, Thanks, everyone. It's a real treat to have the opportunity to provide this presentation today. The outline of the presentation, just a quick introduction of some of the key features of Rodel. Then we'll get into the basis of Rodel, which covers in brief the research behind it, providing an understanding of what's under the hood and why that's important to understand. Then we'll talk about the transferability and validation of Rodel. Are these UK capacity prediction equations transferable to the US and or other countries? We'll have a quick look at some of the comparisons of Rodel's capacity predictions to US field data and work that's been ongoing in that respect. Then we'll get into the program and look at the inputs and the outputs, learn how to drive the program, review the key features of the user interface, and some of its other capabilities as well. And time permitting, we'll do a quick, we'll open it up into a demo of the program. Okay, introduction. Rodel is a program that has an analysis process that facilitates the convergence of design solutions to meet operational objectives. It allows for the exploration and identification of viable alternatives for your given peak hour flows, your site constraints, and your project objectives. It's particularly well suited for constrained high flow locations. It allows for the analysis of flared entries, corridors, and it works well for many other applications as well. It was originally released in 1986 in the UK. It's been used by many agencies and consultancies across the US since about 1992. There was a major update in 2012, bringing the old DOS-based Rodel into the current Windows program. It's been had some major upgrades to include conformance with North American design and analysis practices, such as right-hand drive, English units, US peak hour factor. It includes now a print selection menu for documentation. Importantly, it has maintained its interactive user interface, which is part and parcel to Rodel. It includes two capacity models. It includes the empirical model, which we will talk about a little bit later. It has extended the application of the empirical model to include lane inputs to determine effective geometry, which we will also discuss in more detail. It fully integrates the 2010 HCM capacity model. It provides identical results to HCS. It will include any future updates to that model as well. It now includes full right turn bypass modeling, full right turn lanes, or partial or yield right turn lanes. It has 4 different types of right turn modeling. It now includes the crash prediction models and as well economic analysis to include US and UK intersection and approach level crash prediction methodologies. So your crash and your delay costs are derived from user input values for each. So you choose a specific crash model. You put in the costs per type of crash and or user cost with respect to delay, and it calculates that for you. So it's the Rodel's interface was developed to facilitate understanding of the analysis and to assist in the exploration of the design envelope to arrive at solutions. The inputs and outputs are explicit numerical values. There's no unknown factors. It's designed to inform the analysis or the designer of the geometric and operational relationships. It provides interactive and an educational user interface with its pop-up help as well as the embedded user manual. The interface includes easy sensitivity testing to do what-if scenarios. You can increase or decrease your percentage of traffic for specific approaches to allow for testing of the robustness of a design. You can test with reduced capacity, perhaps due to contextual issues like on-street parking near the roundabout or other environmental constraints. This can allow you to assess the potential for unacceptable queues or delays on specific legs, allow you to then evaluate and adjust geometry to bring those to acceptable levels. And this is completed with the user interface, which allows you to view the input and the output simultaneously. It has two primary modes: a traffic planning mode, which allows the user to specify a target parameter such as delay or a Q or your VC ratio, and then it will give you sets of geometric parameters to meet that targeted user specified parameter. Which I used to use a lot, and when I was an early user of Rodel, and as you get more comfortable with it, I find myself using it less. However, occasionally it comes in very handy, and there's probably applications out there that others could benefit from in respect to that. Most of the time, I'm in the full geometric analysis mode, which is includes, so when you're in the traffic planning mode, then you would then move to the full geometric mode to then refine your geometry, include your bypass modeling, your pedestrian capacity effects. So in some sense, the traffic planning mode has been described as, from a golf analogy, of sort of the drive off the tee, and then the full geometric mode is the chipping and putting. It's fully HCM compliant. HCM and Rodel both utilize what's called time-dependent queuing theory, and it's developed by a U.S. researcher long ago. Delay is derived from the queuing theory equations, therefore nothing in this respect is different from HCM to Rodel. However, Rodel incorporates what's known as high-definition queuing theory equations via time slices. These adjust for varying VC ratios, and the importance of this is that Rodel provides stability over the entire range of VC ratios, even ratios exceeding 1, which provides accurate operational predictions at higher VC ratio conditions. And again, in high flow constrained conditions, that's important. HCM implements a more simplified version of this, and its stability is stable up to about 0.9 VC ratio. So taking a look at the basis of Rodel, and we're going to spend about 10 slides on the empirical model. In the 60s and the 70s, congestion relief was a national imperative in the UK. They had a significant growing automobile use and lots of congested roundabouts, and significant design and experimentation was conducted on these congested, saturated roundabouts. And what they found, which is shown in the graphs on the right hand of your slide here, is that their existing analysis methodologies were not matching observed operations. So they desired an accurate analysis methodology anchored to the design geometrics directly, and so they sought out and set in place a statistical regression analysis approach. And after about 10 years of effort, in 1980, they published Kimber's equations based on a significant amount of saturated capacity data over the full range of traffic volumes from low to high circulating flows. And they rechecked those equations around the mid-90s and found them to be very stable with no changes required. And the stability is attributed to the large statistical data that's collected over the full range of geometry and traffic flows. You can see here on the right in the red box some of the data range for entry width, you know, from 3.6 meters, so a small single lane entry to say a 4-lane entry. Same thing with the road connecting the roundabouts and the other geometric parameters as well. And so in essence what they did was identify the fact that there are a lot of capacity mechanisms that were going on at roundabouts. They were different than what they could then signals or stop controlled intersections. So because of that is the reason they went to the empirical approach and the regression approach. And so they were wanting to capture the differing driver behavior described directly by the different geometrics of different sizes and shapes of roundabouts. And this was a significant departure from their existing procedures. So at the end, what they ended up with, they started with 35 geometric parameters, and they regressed these down to 16, and then to 9, and then finally to the 6 most significant. So beginning with V, which is referred to as the approach width. These are the 6 parameters that are entered into Rodel. Your entry width, E, and the distance over which you would flare. For example, if you had a multi-lane approach, a 2-lane entry that was being fed by a single-lane approach, the distance over which you flare from that single-lane approach to the 2-lane entry. In addition, you enter the radius as well as the entry angle, referred to as phi, which is described as the actual angle there is 2 phi. So the entry into the program is half of that measured angle. It's a little confusing, but it's and then the diameter finally. And we'll look at each of these geometric inputs here a little bit more carefully, because each have varying. I'm just going to try to find the. Do I have? Where's the old file? No, the pointer. Here we go. Spotlight. All right. Got the spotlight, and hopefully I can advance the slides with the spotlight on, and doesn't look like that's the case. So anyway, I'll just use my cursor arrow. The 3 major capacity variables are the entry width, the approach width, and the flare length. So these are reflected. E, as you can see, when they plot the entry width on the x-axis compared to capacity on the y-axis, it goes up at a nearly 1-to-1 value. So E is very sensitive to capacity. More entry width, more capacity. V, similarly, goes up at nearly 1-to-1. And it is also very sensitive to capacity. And then flare length goes up very steeply. It's the length of the flare versus capacity again on the y-axis. But then it breaks. There's a breaking point at which it falls off. And so adding more flare over a certain distance provides no value. So it's important to understand that. So those are the 3 major variables that affect capacity. Then the radius, the phi angle or the entry angle, and the diameter are minor variables. And if we look at these individually, the radius here in the bottom left, that goes up very sharply, and again, that breaks. So, radius is over that distance, there's no benefit, and so understanding that is important in the design process. And then phi angle also has a minor influence to capacity in the sense that the steeper the angle, the more perpendicular the entry, the less capacity you get. And diameter is interesting, and in the fact, so there's a graph here that shows a 180-foot diameter line and a 300-foot diameter capacity line. And what you find with D is that at low to mid circulating flows, the capacity there again is on the y-axis. At low to mid circulating flows, the diameter has very little effect on capacity. You can see, from 180 feet and going to almost doubling the diameter, very little increase at the mid to low. But by contrast, so there's the capacity, very little increase. By contrast, at high circulating flows, when you're challenged in a design, there are times when understanding this can be quite useful, because at higher circulating flows, this shows where that same increase in size of diameter, you can have a doubling of capacity, in that case, at the high circulating end. So these are the 3 major variables that are used in Rodel, which again is V, E, your approach roadway width, V, your entry width, E, and the distance over which you widen from V to E. And so those are the essence of Kimber's equations. And again, there's the radius and the entry angle. So understanding these various capacity mechanisms allows for convergence of desired operational objectives within the available space and context. You're looking to avoid under-design with early congestion, poor public opinion, etc., or over-design, which gives you more capacity than necessary, more entry lanes, perhaps larger, faster, perhaps less safe geometry, It could affect your feasibility, such as greater impacts, more right-of-way, higher costs. So moving to the next section titled U.S. Validation and Transferability for North American Practices. So early on, it's often, I struggled with this part of the presentation because not knowing the familiarity with the history with these programs and the issues here within the U.S., but it's often been discussed and thought that UK drivers are more accustomed to roundabouts because they have lots of roundabouts producing higher capacities, and it seems like a reasonable thing that would be true. Perhaps they have different types of cars or trucks that would affect these, and to some extent this may be slightly true. But what was reported early on, U.S. researchers were confusing U.S. and U.K. design practices, and it refers to effective entry width versus actual entry width from a capacity perspective. And so the U.S., we have widened entries shown by the red arrow here in the photo, that if you put that into the old Rodel, DOS-based Rodel pre-2012, you'd get capacities up at this red dashed line of about 1,800 vehicles per hour, which is, you know, around 700 vehicles per hour more than what we had been finding in the U.S. What was not understood was in the U.S., that is what's referred to as non-effective entry width. And so the effective entry width is that shown in the yellow arrow at the entry, and you can clearly see we have a single lane circulating and a single lane exit in this case. So you needed to understand the differences between the two. These were often confused, and it was some confusion. The new Rodel avoids all this. It now has bi-lane inputs, which determines your effective geometry, which will avoid the incorrect use that could have occurred with the previous version. And interestingly, when you look back at Kimber's data and the data collected in the UK on a small single lane entry roundabout, their data and was almost identical, very identical to our US data for small single lane roundabouts. And that's, so if you look here at a flared entry design, now that's where you're getting about the 1,800 vehicles per hour intercept that was being, that had been incorrectly predicted for a single lane roundabout. So what that's actually modeling is a true flared entry roundabout, which is shown here on the right. And this is some FHW data. There's a separate work effort ongoing, TOPR 34, which is going to be used to develop a new updated HCM model that may be out in 2015 or early 2016 is my understanding. But with the understanding, we've separately looked at their data to try to compare Rodel's predictions to this data. And on the left, you see what I'm calling an urban single lane roundabout. It has a little smaller diameter, tighter entries, tighter radiuses, and it gives a capacity line. Those capacity data is in the gray dots in the graph below. And on the right-hand side is a larger curvilinear single lane roundabout, which gives a higher capacity. And so Rodel is able to capture the various capacity mechanisms that are occurring even within just a single lane design, from a smaller urban compact to a larger, more curvilinear type of design. And that's just overlaid with the original data there. And so this again is a graph used by permission by FHWA that these wanted to just reiterate that there is an ongoing effort separate from what I'm showing here, of course, that is going to be used to develop a new FHWA HCM updated model. But what they're finding in this work is the dashed line here is the HCM 2010 capacity, and their data that they collected in 2012 is showing when they plot lines to that data, fitting lines, either straight or curvilinear lines, they're showing an increase in capacity. They're getting better data than what they had in the early 2000s, which formed the basis for the 2010 version. And so Rodel allows you to easily, and we'll look at this and look at the X and Y intercepts of the capacity that's prediction. You can easily compare how Rodel is predicting compared to the US data. And so this is for a two-lane entry roundabout. This is one lane of a two-lane entry roundabout, and Rodel is right there with the US data. And so that gives us a lot of confidence in its predictive capabilities. So Rodel can be used for analyzing all types of roundabouts, from small urban compact with very perpendicular entries, small entry widths, and it'll account for the capacity effects of that type of a shape. And then it can also account for the operational output and prediction for a larger curvilinear type of design. And moving to a more multi-lane, again, you can have a wide variation in application types. With single, multi-lanes, various types of right turn bypass lanes, in hybrids, turbos. So Rodel will capture the operations of these various types of roundabouts. And again, giving you a high level of confidence in the traffic operations side and the predictions of what you're doing. So just a few quick examples, the inputs that you put into Rodel. Here's a single lane, so you'll be identifying a single lane approach, a single lane entry, single lane circulating, and a single lane exit on this type of a roundabout. And in this type of roundabout, you'll also be identifying a single lane roundabout, but you'll put in a full right turn bypass lane, and in this approach, a partial or yield right turn bypass lane. And then moving, you can analyze roundabouts in series, and these two roundabouts represent most of the variation in roundabout design, which is to say two-lane entries fed by two-lane approaches, flared entries, single-lane entries, all contained within spirals within these two roundabouts. Yield right turn bypass lanes and full bypass lanes. This is a three-lane entry, with a full right turn bypass lane. Rodel can model up to 4 lanes of entry, which is rare, but occasionally occurs. And here's a flared approach. So your approach roadway width V, your entry width E, your distance over which you're flaring. You're going to identify a 2-lane circulating and a 2-lane exit as well. And if you don't identify these correctly, we'll talk about this in a moment. Rodel gives you error messages within its pop-ups, and it doesn't allow you to make the mistakes that were occurring with the previous DOS version occasionally. So a program over here, let's learn how to drive it a little bit. The user interface is a really important component. It looks pretty, there's basically, so we'll look at the empirical model, and then which is you have your first row of information is your geometric row. Your second row is your traffic flow inputs, and then your third row is the results or your output. And so this is the user interface where you're able to put in the geometrics and see what's happening from an output perspective in this results row simultaneously. So that allows you to test for the what ifs and and get a feel for what geometry can work for your situation. And here's a screenshot of it in the HCM mode. And so the only difference is HCM only has the lane inputs, and then the critical headway and the follow-on headway inputs as well. And there's calibration for each of the two programs. So again, there's your geometry input, there's your traffic flow, which is identical, and then your output. And so you can toggle between the two models within the same project and to compare and contrast how one is comparing to the other. You have your project information up on top. It can allow, your print menu. You can add or subtract legs. You can add notes. You can view your exit flows. You can view the operations in various time slices, from a 15-minute time slice all the way down to a 1-minute time slice, to understand the rise in the flow of traffic through the hour. This is where you choose the type of flow. You put in either a peak hour factor. You choose your model. You can choose queuing or control delay. Then you choose if you're going to use peak hour factor, which is most common in the US. It also maintains the UK direct and synthetic modes. The direct mode is an area that doesn't get much discussion, but we're starting to use it more with analyzing existing roundabouts, and it could be very useful for capacity research as well. You also choose your peak here in the top row. Again, your geometric inputs. Rodel now includes a geometry editor, so if you click on one of these three boxes that are highlighted in the cyan color, you get a geometry editor, so you can add your geometry and your lanes visually as opposed to numerically in the columns. Then you go to we have secondary inputs, which includes calibration for each model type, and your crash and your economic and your bypass inputs. And so we'll take a look at bypass calibration and the safety and economic analysis. So when you press on those buttons, you pull up your calibration for either model that you're working in, whether it's the empirical model or the HCM model, and you can calibrate for each. Again, each has pop-ups, user help pop-ups to provide you with a quick summary of what each thing means, which becomes very, very useful through the course of understanding what you're doing. You have the HCM calibration as well for your two. You can do calibrated values and save those calibrated values for as well and use those. Accident model, you choose an accident model. There's the U.S. NCRHP 672 preferred vehicle model that can be that has been included with the UK pedestrian safety model. You can use the vehicle model by itself, or you can use the UK empirical model and look at crash analysis. It gives you, the output gives you just the crash numbers. It also, the program will give you it in rates per million entering vehicles as well. And if you don't have, it uses 24-hour ADT values. If you don't have those volumes, if you have them, you put those in. If you don't, if you want to just get a quick feel, it'll synthesize the ADTs using the rule of thumb, 10% of peak for ADTs as well. So it's a quick and easy way to get a feel for that. On the bottom is some of the outputs that you see in the program. Approach crashes, entering circulating crashes, exit crashes, all crashes, and PED crashes. And so under the economic evaluation box here is where you put in your costs. I've input some numbers here, $1 million for a fatal, 500,000, and so on and so forth. And you can also put in a cost per hour for delay, and it calculates that for you. Here's the bypass input menu for the type of bypass. You choose if you're using a yield or a full bypass, and then you have all the geometric inputs as well that you place into the program. It can model full bypass lanes, which is represented on the left here with a free downstream receiving lane that doesn't end, or it also models a merge condition, and you put in the values for the distances, and it will provide calculations for that merge condition and give you messages with respect to the appropriateness of that merge downstream. It also does bypass lane types, yield bypass, so a right turn lane that comes to a yield line, whether it's separated by just paint or a raised auxiliary island or painted gore. It has 3 different types of yield lanes. It also can allow you to model dual right turn yield lanes. So this says 1 or 2 lanes. That can be a dual right turn lane, which can come in handy in some situations. Moving to the results part of the user interface, gives you your flow rates for your entries and your bypass, or your opposing or your circulating flow. Gives you your capacity, your VC ratios, your average delay, your max delay, your 95Q, and your level of service based on signalized thresholds. It also, you can easily just look at your intercepts from a capacity perspective, your y-intercept and your x-intercept and the slope of the line, which we looked at a little bit earlier. In the accident, if you choose crashes or accidents, you get your accident output, approach, entering circulating, exit, as well as the crashes per million entering vehicles. And then you can have your economics, you can have your delay costs, and your accident costs, and your total annual costs calculated for you as well. And then your global performance includes everything into one output. So we'll talk briefly about the embedded pop-ups that are part and parcel of the program. So for example, if you click on E when you're in the main screen, you'll get these pop-ups that describes what E is. It gives you the ranges of values. Same thing for all of these, L prime, all the 6 geometrics, you'll get a quick description of that. And then the little question mark there, if you want more information, will send you to the embedded user manual, which provides more information and more description about each of the inputs. It also now gives you error messages. So if you have, for example, a 2-lane entry being fed into a single circulating lane, it'll tell you that you need to change that, and that's a warning message, or excuse me, an error message, and it won't allow you to run the analysis. So it gives you, sometimes it'll give you error messages for certain incorrect inputs, and in other cases it will give you warning messages. It also gives you the same error messages in the HCM model mode, so nothing in that respect is different. And then it also will give you warnings, you know, to give you, hey, just give you a heads up on certain things. It still allows you to run things, but it gives you a heads up to maybe take a closer look at certain things. It may be okay, it may not be okay. Some of the warning messages that it you know, can give you: exit leg, circulating, different types of warnings. With that, if there's time, I could pull up the program itself and run through a few things. If Lisa, if you could tell me how much time I might have available, if any.
Sure. You actually have about 8 to 10 minutes to run through a demo, if you'd like to do so. Great.
All right. I'll probably take maybe 5 or 8 minutes and do that. So I'm just going to open up the program. And go ahead and, well, you can open an existing file, or you can go to a new program. I'll just click on new, and so you choose, for the US drive on right, you choose 3 to 6 leg roundabout. You type in your project name and project information here. Then what? Choose your model type. I guess I could just go through the top row of information, and you know, here's your typical, you know, information up here. Here's your printing. You can do a print preview, and here's the print menu, which gives you the and you can choose what information you want printed out. There's quite a lot of different outputs that you can get for reporting purposes. Here's the choose your delay, queuing, or control type. Here's the 2 different modes where I talked about: the geometric mode, which gives you the full geometry here that you're working with, or you could specify a delay. So for example, if I specify a delay, you know, maybe just to give some, you know, you can choose any kind of types of delays that may be acceptable for the condition. You just choose a diameter that might be reflective. This is just a planning mode, and you would enter your capacities. I'll just, you know, throw a few numbers in here just for try to get it to. And I should mention maybe at this point the way you enter your flows. It starts, because I've chosen I chose a 6-legged roundabout, and so that actually, you know, so instead of saying lefts, throughs, and rights, if you have a 6-legged roundabout, you have to start with your first movement, which is your U-turn, and then your next movement, your next leg, and then following on down to the right turns, and then you have your bypass entry as well if you were to use a bypass lane. If, for example, we were to open up a four-legged roundabout, then you can see you have U-turns, and then your next movement would be a standard left, your through, and your rights. This is where, up here is where you put in your legs. So I'll start with northbound, and then it goes counterclockwise. So this would be westbound, southbound, and eastbound. You put in your bearing in terms of if it was not a standard cross 90-degree intersection, you may, that is taken into account in the UK safety equation. So it's the only place that would be included. This is where you put in your approach roadway width. So if you have a 24-foot two-lane road approach, it's typically going to be, it could be 20 to 20, typically 24. It could be a little wider, but typically often we use that. And this is where you would enter the number of lanes. So you identify one. If I have one in here, it'll give me some kind of a warning that something's not right. So I push it back. Here's your geometry inputs. I was talking about if you were to specify different delays, you could put in different delays, put in some traffic, and try to get it to. I'm going to go ahead and choose I'm in synthetic, which is the UK methodology, which is a pretty refined way of modeling the rise and flow of traffic over the hour. If we put in a peak hour factor, more consistent with our US practices, and if I hit run within this planning level, and I can go up here to this icon, which is the view entry geometric options, it will give me different entry width and flare length options to achieve that targeted delay. And so you can target Q length, you can also target VC ratio. Often, as I mentioned, I'm usually working in full geometry, and so if this was a single lane, this would be just a 12-foot entry typically. It could be a little narrower, and that will affect geometry to some respect, and you identify the number of lanes. This would be a flared entry if we're going from 1 to 2, and then you'd have a flare length. There's your pop-ups describing each one of these inputs as well. Okay, I had a 1 in there. What else? So if we press, here's the results at the bottom. So you can look at 15-minute results consistent with U.S. practices. You can look at the delay and the other measures of effectiveness over the whole hour versus just the peak 15-minute. And then here's your slope and intercept tab, your economics tab, your global results tab. So here's the bypass entry. If you were to look at entering bypass lanes, it would you choose the type of bypass that you're using here, yield, for example, and if it'll tell you you've got 0 flows on that leg. So there's a lot of checks and balances within this. Here's your economics input. So we talked about adding your user costs in here, for fatal and different types of injury crashes, as well as pedestrian crash costs, and your delay costs go up here, cost per hour if you wanted to do some economic analysis. Your calibration tab, we're in the empirical model, so this is the empirical way. If you click on the icon, the pop-up, it'll give you a description of how you could potentially adjust the slope and the y-intercept to more closely match observed.
And Mark, this is Lisa. You have about 2 minutes to wrap up. Thanks.
Okay. Yeah. Your truck percentages. Here's the factor. Here's a couple of the sensitivity features that you can use in the factor. You could just do what happens if I do a 10% increase? What if this is lower at 10% lower? What if this leg had a 20% increase or a 100% increase? And you can run that and quickly see the effect of the geometry that you have input on the output and the operations, and then you can go back up to the geometric mode and make some adjustments and again hit run and see what those changes would be. And I guess with that I'll just end it and say thank you.
All right, great. Thanks, Mark, for your presentation, and I'm going to pass it now to James for the next presentation. And just want to remind our audience members that we are receiving lots of questions, but we will be tabling them until after both presentations are over. So with that, James, we do see your screen. You're pulling up your slides, so you may begin at this time.
Thank you very much, Lisa. Good afternoon, everybody. Before I start off, I'd like to thank also TRB for allowing us the opportunity to present during the series of webinars. Just a brief introduction of myself. So I've been a traffic engineer for the past 15 years, and I've been working within the Transport Research Laboratory for 6 of those years. I have a split role, so I work on the consultancy side of the business, so I use our software and the Arcady software program to do consultancy, and I also work on the development of the software and the model, so I'm the technical referee for that software. So without further ado, we'll progress with the presentation. Just a quick, brief introduction to the elements we're going to cover through this webinar. Obviously very similar to what was just been presented. A quick introduction to the background and the theory of the Arcady model, the inputs that you need to put into the software to actually develop a basic model, a step-by-step guide of that data input, some of the output facilities that are embedded within the software, and how those outputs can be analysed, and some of the functions of the software that allows you to easily access the results. Excuse me. So the Arcady model and capacity software has obviously, well, the model itself has been used in the UK for the last 40 years. It's based on extensive research. It uses the empirical formula to calculate the capacity, say, of each arm of a roundabout, of the function of that geometry and the circulatory flow crossing that arm. So the capacity creation is derived from an extensive amount of research. There's lots of different junction parameters, and obviously the most parameters which had the greatest impact on geometry were the ones that were taken forward and included into the actual model. Obviously, on top of the capacity model, queues and delays are also calculated using the time-dependent queuing theory. This method treats the whole range of demand and capacity and takes proper account of the statistical nature of traffic and the variations with time of demand and capacity. As the slide shows there, so obviously during the development of the capacity relationship, we looked at a total of 86 different roundabout entries, over 11,000 minutes, and 500,000 vehicles observed. So in essence, our capacity empirical model was actually validated against real life traffic sites. So we're very confident that the actual model gives a good prediction of the capacity that you observed on site. We also reviewed those relationships in the 1990s to ensure the appropriateness of that model, and also it was found to still be accurate. We've also managed a number of different other capacity projects which looked at large and grade separated roundabouts which have a slightly different capacity relationship, and we also looked at UK style mini roundabouts and developed a capacity relationship for that. We've just finished a research project where we revised the mini roundabout UK model, and that was obviously included in the latest release of the software. So these are the capacity models currently accessed within the latest version of Arcady. Obviously you have the normal standard roundabout capacity model. Large and grade separated roundabouts have a slightly different capacity equation applied. So there was 2 research projects undertaken on the larger scale roundabouts, and it was found that there was another couple of one geometric input and another flow input that is required to accurately model those types of roundabouts. UK style mini roundabouts. We also have within the junction software for Arcady itself, Arcady software, the HCM 320 roundabout capacity model, and we just implemented in the Arcady 9 the all-way stop and two-way stop. So you could basically build the 3 different types of junction in the same file, apply the same flows to each junction, and then you can do a direct comparison of the alternative intersection configurations to try and determine your best intersection type. And another recent addition to our capacity models are what we call the lane simulation. So this allows the user to model, as opposed to the whole road, the whole width of the road which the empirical model runs to. The lane simulation will allow you to model each lane on a lane-by-lane basis. So if you have unequal lane usage, or if you want to try reassign your pavement markings to try different destinations for different legs, then obviously you can run the lane simulation to see what effect on capacity your lane assignments might have. Excuse me. Obviously, these are different types of roundabout that can be modelled within the software as well. So, obviously, single at-grade normal roundabouts, whether these are at-grade, whether these are compact single-lane entries or wide 3-lane entries, with or without flare, it can all be modelled within the Arcady software. Obviously, like I said, it can do large and grade separated roundabouts, mini roundabouts. You can have a roundabout with between 2 and 20 arms. You can link roundabouts or have a network of linked roundabouts in a system, and again, you can model each roundabout, any type of roundabout, using the entry lane simulation mode. A few quick slides based on the principles of the program. So obviously, as I said earlier, the program uses an empirical formula to calculate the capacity of each roundabout or each leg of a roundabout as a function of the measured geometries and of the circulation flow that's passing through that arm. So obviously this is the standard formula which represents that calculation, where obviously QE is the entry capacity, QC is the circulation flow, and FIs are the intercept and the slope that's been calculated. So basically they are constants determined by the geometric characteristics of the roundabout itself. So the capacity formula obviously used within the software is linear in nature. Obviously we consider to have a slope and intercept. So obviously the intercept is on the y-axis, and that is the maximum capacity that can travel through an individual leg based on your entered geometric parameters. And obviously as your circulation flow increases past that leg, then obviously your capacity will actually decrease. Obviously when we did the research for all those 86 sites, originally all these graphs would have had similar vague plots, and obviously that's how the linear regression model was then developed over the whole range of all the sites that we looked at. Obviously another basic component or principle of the program is the relationship between the circulatory flow and the entry carriageway and the interaction between the arms. So the circulatory flow across any entry is derived from the entry flow and the turning proportions from the other arms for the other legs of that roundabout that you're investigating. So obviously the circulation flow is derived, and then during an Arcady run, an iterative process is developed, and it's used to calculate the final entry, circulatory, and exit flows based on your demand and inter-turning proportions. So looking at some of the critical inputs that are used within the Arcady software now. So as we said earlier, Arcady predicts capacity as a function of flow and geometries. So to do a basic, obviously Arcady roundabout model, your basic entry requirements would be measuring and entering your 6 geometric parameters, which we'll discuss a little bit later. You need to enter the demand for each leg, the turning proportions for each leg, and if you have them, the heavy vehicle mix as well. That's the basic data entry that's required. Obviously, there's a number of more advanced features that you can utilize within the software. So basically, on completion of doing your measurements, whether that's by hand or by CAD, it should hopefully just take between 10 and 15 minutes to set up a basic Arcady file. So one of the critical inputs that you need to input into the Arcady software is vehicle demand. One of the main causes of error that people that some people do when entering demand is they enter their turning proportions rather than their demand. So demand is what vehicle is demanding at each leg within a certain time period, whether that's at the front or the back of any queue. So if there's any queuing within a 50-minute time segment, that those vehicles need to be counted as demand as opposed to carrying it over to the next time segment. Excuse me. So like I said, any demand should be counted at the back or upstream of any queue. There are a number of different, what we consider to be traffic profile types for which you can enter into the software. Obviously, these are the 6 major ones you could do. Direct data is where you enter, so if you've taken 15-minute traffic counts from site, you can enter those 15-minute time segments directly into the software, in which case you are more liable to accurately represent what's observed on site. If you choose the levels mode, this is where you, as a user, enter the pre-peak, the peak and post-peak flow levels. So you enter your time for when those 3 elements are going to occur, and from that it will derive a non-symmetrical traffic profile type for each leg in turn. Sometimes you may want to use the 4-hour profile type. So this is where if you have a prolonged peak period over a number of hours, you can enter 4 consecutive hourly counts, and then basically it will then derive a symmetrical curve based on each individual hour count. 1 hour is probably the most commonly used traffic profile type in the UK. It's where you enter 1 hour's value, 1 hour's worth of traffic flow into the software, and then from that it will derive a symmetrical peak around the central period, and obviously your queues and flows a normal peak through that. Your queues and delays will obviously generally rise and fall in line with that assumed peak profile. Obviously we've included the PHF traffic profile type, and lastly you can use a flat profile type, so you use one number, one flat profile, one flat value, and that's used throughout each time segment, and that's can be a very quick and easy way of doing a very easy basic run to see what type of flow levels can be put through roundabout in order for it to work or fail. In addition to entering accurate demand, we also need to enter accurate both turning proportions and heavy vehicle mix. Turning proportions obviously specify the traffic that turns in each direction from each leg in turn, and obviously these are obviously needed by the program in order to calculate the circulatory and exit flows, which are in turn then used by the capacity calculations. And obviously it's relatively essential that this information is correct. The measurement of turning proportions can be treated as a separate exercise from the measurement of demand, but ideally they should be measured at the same time. Percentage of heavy vehicles, again, if you have the information, it's always useful. Obviously, the more heavy vehicles you have traveling through a roundabout, the greater effect that's going to have on the queues and delays. Next few slides, we're just going to go through and start looking at some of the geometric inputs that you need to put into the model. So these are what we consider to be the major geometric parameters. So these are, as Mark was saying earlier, in the original research, there's over 35 parameters. This was narrowed down to try and find the ones which had the most impact on the geometric parameters which have the most impact on capacity. So these are the 3 parameters which have the greatest effect on capacity. The first measurement is what we call the approach width, which is B. So this is taken upstream of any flaring, so where your curb line and your median line become parallel sided, you take a straight measurement across the road. Your entry width E is replicated by the line A to B on the screen. Excuse me. That is basically taken perpendicular to the curb from where your yield line joins the island or road marking. Obviously, when doing this, it's always imperative to understand that we need to measure usable road width. So basically, as Mark was saying earlier, if there is any hatching or you have a hard shoulder or a hard shade on the inside or in the median, then obviously that's removed from any measurements that you take, because you would in those situations you will be likely to overestimate capacity. And the last of our measurements is what we call the flare length. And this is basically, this is the distance over which effective flare develops on the approach to the roundabout. So in essence, in order to do this measurement, you take your approach width and you just measure from the median towards the curb line to give you A to D, which will then leave you with B to D, sorry. You divide that by 2, and then from that measurement, you then measure out from the curb until it joins your tram line, and obviously that then is there just a direct measurement of your flare length. I mean, obviously some of the geometric parameters, some of the measurements can be quite tricky to do when you first get started, so once you've done a few, then it's relatively easy to pick up. Obviously a lot of people use CAD or other types of other software to obviously do these measurements, so to make that a little bit quicker. So those are the 3 major geometric parameters which have an effect on capacity. So we'll start looking at some of the other ones. So these are then what we call our 3 minor parameters. So these, although they have some effect on capacity, they won't have quite the same effect as the 3 major parameters. Entry radius is basically measured by taking a 10-meter measurement upstream from your yield line into the roundabout or next arm, 25 meters back from your yield line, and then it will then just be trying to find within that 35-meter length of curb line the 20-meter length of curb which has the minimum radius. So it sounds a little bit complicated, but it is relatively easy, or once you've done a couple, it's relatively easy to pick up and follow through. The next one that we consider is the entry angle. So this is these 2 lines here. So basically this, in essence, all you're measuring is the angle between the mean path of vehicles entering the roundabout and the mean path of vehicles in the circulatory carriageway or exiting the roundabout. Obviously, a lot of these factors will have an impact on capacity, but obviously they will also have an impact on safety. So obviously, conflict angle or entry angle of the roundabout obviously has an impact on the safety operation of your roundabout as well. So having a very shallow or very large conflict angle will have, although it may help in the long run, in some cases your capacity, it will have a detrimental effect on roundabouts. In some cases, it's generally finding the balance between capacity and safety in some instances. Obviously, and the last geometric measurement that we need to take is the inscribed circular diameter. So this is the diameter of the largest circle that can be inscribed within the junction outline. So again, it's ignoring any road markings or spiritual islands. In most cases, it will be where the outline is symmetrical. So if it's a symmetrical roundabout with all 4 arms parallel, it generally just be a 1 value for each leg. If you have a non-circular roundabout where you have a heavy oval in design and shape, your inscribed circular diameter will generally be different for each leg in turn. So basically, it's how, in many ways, it's how the person approaching each leg views that roundabout, so how open or how closed off it appears to use it on approach. So those are the main critical inputs into developing an RQ roundabout model. Accurate demand, accurate turn proportions, and then measuring your 6 geometric parameters. So that's the 3, say, 6 or 7 basic elements that you need to set up and run a basic RQ file. I'm just going to go through a step-by-step guide for data input and how you go about entering all this data into the software. When you first open up software, you'll be given a startup file or startup window. So this allows you to choose which type of junction you want to do, how many, if it's a roundabout, how many arms or legs are present at that junction, what roundabout capacity model you want to use, and how many demand sets, so whether you want to do just a single or whether you want to do an AM and a PM. So basically, just by using this setup window, it will then set up some of the basic information to save you a little bit of time as you then get into developing the rest of the model. Obviously, once you've selected your junction type and the number of arms, etc., you will be open up the screen, and basically it will firstly start off with just the data outline open. So data in junctions or arcades is organised in a hierarchy. All of the data input and virtually all the outputs can be accessed via the tree view data outline. It's just a case of expanding these plus points, and basically it will allow you to find all the geometric data inputs, all the that are needed to actually build the model. Although that's where a lot of the information is held, it's not imperative that you use the data outline screen to construct or edit any of the files. It basically provides a summary of the data in the file. There is no set structure as to how you build an ARCHI file. Basically, we've listed we found over the years that people tend to work in different ways, and that some people prefer to work in a structured way, some people prefer to work in their own methods and their own styles. So we've left it relatively open as to how people want to actually construct and build their files. But there are a number of obviously shortcuts and items that make it easier for people to develop their files. In this case, we generally, the icons on the left-hand side of the window will basically take you to all the relevant data entry points to run the basic file. So your junction, your geometry, any pedestrian crossings, your OD turning proportions, traffic demand, vehicle mix, and then you can use it to view your results as well. So in many cases, it's just a case of opening the file, setting up your analysis and demand set, so how many different sets of geometries and flows you want to model, and then it's then just a case of selecting the icons down the left-hand side, entering the relevant data, and then running the file, obviously using the run model icon at the top. In many cases, if I'm building a model using the system, I will generally have the diagram open, which is a top icon. So when you select certain geometries or turning proportions or flows, this will then highlight the respective arm of the roundabout you're modeling, so it's very clear and it's very easy to understand which arm you're entering data for. So basically there is a kind of like a step-by-step guide that you can follow to set up a basic file. It's generally what we call FAD icons, so it's file description, analysis sets, demand sets, and then follow those vertical icons down. So the file description is just basically where you enter your basic job details, so job title, location, relevant site numbers, who the client is, your basic data, your basic entry for each individual project. The next step, working down your data outline, would be to set up your analysis sets. So the way analysis sets work is that it allows you to set up a number of different geometries or properties of junction and then do direct comparison within the same file. So instead of setting up a second file with a different set of geometries for the same junction, you can set up maybe a baseline existing layout, and then you can set up a second analysis set, and this will then allow you to build a second set of geometries, or maybe just changing the geometries of one arm or one leg, and then running that and doing a direct comparison within the file. So it saves you a little bit of time of setting up different files or setting up a different number of the same junction within the same file. Your next step then is to basically set up your demand sets. So the demand sets are how you enter your demand data into the software. So in this case, it's just a case of you enter your traffic profile type, so whether it's the 1 hour, the direct, your AM or PM. Obviously, you can have 15, 20 demand sets if you so wish, so you could have baseline, AM, PM, traffic, growth, as many as you basically need. We've seen a number of files with maybe 20 demand sets included, so it's a fairly robust way of entering this information into the software. So once you've entered your analysis sets, you've entered all your demand data into the software. It's then just a case of, this is if you're setting up a basic file, you kind of come to the end of the requirement to enter your data into the data outline, and then just be a case of moving on into your following the vertical icons down the side of the software. One other step to try and remember is to set the unit types. It's always best to set the units before you obviously start entering demand to make sure, or geometries to make sure you're using the correct inputs, so whether that's vehicles or PCE for demand, or whether you want to obviously meters or feet for geometries, and how you want the results to be shown as well. So whether you want your results in vehicles. So always an idea to try and set up all of your units before you start entering the main components of the data entry. So once you've set up all of your functions, your analysis sets and demand sets, it's then a case of following that vertical toolbar down. So you open your intersection window, make sure, set up, make sure you have the correct intersection type selected. It allows you to have the order of the legs. If you have one or two junctions within the file, you can select copy flows, and basically if you have a roundabout and a two-way stop within the same file, you can copy flows from one junction to the next, and then you can do your direct comparison. Your next icon then down would be your geometries icon, and this is where you can enter your relevant geometric parameters which you've already measured. A lot of these data items or data editors are compatible with Excel formats, so you can, if you have your demand or some of your geometries already set up with an Excel spreadsheet, it was just a case of copying and pasting some of this functionality across to obviously try and ease the time that you need to develop and build your files. So once you've entered your relevant geometries, you can then add a crossing if you need to. So you have a choice of unsignalized or signalized crossings. So once you've then developed into your geometries, it's then the case of entering your relevant traffic demand, tone proportions, and vehicle mix. So these are your next icons down. The flow window, basically all your demand is the window on the left, and this basically allows you to either enter the hourly average demand within this window, or you can select to use the OD tab. So basically in this instance, the OD tab has been selected, so then it allows you to use your OD destination to enter your demand for each leg in turn. And conversely, similarly, you can then enter your vehicle mix again for each leg in turn. So to the first, second excess. If you have decided to use the direct method of data entry for your demand, obviously both your toning proportions and your vehicle mix can be entered for each 15-minute time-second period. Obviously, if you do want to use a demand process, obviously it is potentially the most accurate for predicting capacity. Like anything else, the more data you put into software or any model, the more accurate the results are going to be when you run the model. The only thing would suggest is that if you are using demand, that you take the average of demand for each 15-minute time period over a number of days, as opposed to just a single day's worth of demand. If you're using a 15-minute time segments for that traffic profile type. So basically, once you've entered your geometries, heavy vehicles, your flows, it's then just a case of obviously running the file, and then as soon as you've run the file, a summary window will appear, and obviously this will allow you to see, in many cases, the worst results for each leg in turn. Some of these results may be from different time segments within the model, depending on which traffic profile type you're using. But basically, this will just give you the worst results for each leg in turn, and obviously then it gives you a very quick and easy idea of what legs are obviously performing worse, and then obviously where you need to try and improve the roundabout. we're just going to have a quick few slides on looking at the output of the models and the accuracy and reliability of the results. Obviously, like any data input, if the data is input at its coarsest level, so using all the default options available, then obviously the results you get back are going to be at the coarsest level as well. So we always say that default values within the software should only be used, or should be used with great care, and only when it's impractical to obtain better data. Sorry, excuse me. So where possible, the accuracy and capacity and delay calculations for an existing intersection may be improved by the use of local traffic observations. Obviously, there is a functionality within the software called the analyzer screen, which allows you to do quick analysis of the results, to look at, to check the robustness of a particular design. So slight variations in geometries can be tested and analysed within the software. And obviously, the use of the program should be limited to situations in which the values of the geometric parameters lie within the ranges over which they were obviously developed and observed within the initial research. Once you start entering values which are outside the bounds of that original research, you will generally get a warning within the software saying that your flare length exceeds a certain distance, and obviously you need to treat the results with care. Generally speaking, at a general site, the standard area of capacity prediction for a standard roundabout from the mean point is about 15%. This standard area takes into account both the random variability between supposedly identical sites and the random variability that may occur at a single site at a different day. Capacity can be checked, so traffic observations are made when a particular leg is operating at capacity, and that results in correction to the capacity. So basically, you're then changing the capacity to observe values and then getting a better prediction from the model. This technique improves the accuracy of modelling by eliminating that site-to-site variation that's implicit within the capacity equations. So basically, after you've run the model, you can choose to generate a report that summarises all the input data and results. The report is in HTML file, is automatically saved to disk, so all the results are saved automatically within the same file. So you can generate a report, and you can convert that to PDF or Word. It's quite customizable, so it allows you to set up what tables, what needs to be presented in a report. And excuse me, there is within the system that allows you to compare separate files. So if you have you can copy a file, make some changes in one, run a report, and the report will actually display in different colours all the different variations in result between the two systems. Some of the output facilities is that there's something that we call the residual capacity mode. So basically, Arcady can assess the network's residual capacity. So this is a user-defined threshold. So this is basically a measure of how much more traffic the system can cope with before a user-defined threshold is reached. Obviously, in the sum window shown here, obviously this has actually got a negative value of -13%. So this is saying that based on your current turning proportions, you need to remove 13% of your flow from leg 3 to meet your user-defined threshold. So this is a very quick and easy way of seeing what needs to be done capacity-wise or flow-wise to try and resolve any capacity issues that you may be having. Obviously, results can be viewed in a data editor or via the summary results screen, and you can also use the analyzer screen to study the effects of the various inputs and changes on results. So the reports are intended to list all data inputs and outputs, although these are customizable. So normally you want to see the results immediately without having to generate those reports, so that data is available first via the vertical window, which I'll run through with you later during the quick demonstration. We also have the junction diagram has the ability to import, say, background aerial images or JPEGs or roundabout designs. So basically you can then set up a scale within that system, so you can, if you know a defined measurement, you can set that scale, and then basically then you could then use that image to show, in this case, queue lengths. Obviously these are the queue lengths that have been scaled to a set distance. So the red is where the queue is extended to, the green is where it's coming down from. So you could potentially use your junction diagram as a way of visually displaying the results that are available to you. So this will just be a very quick and easy way. So this can be copied and pasted from the software into Word or onto demonstration boards, and it's a very quick and very visual way of demonstrating to people the predicted length. So this will display your predicted maximum queue or your predicted 95th percentile queue as well. So it's a very quick and easy way of displaying that information to other users. We also have what we call the analyzer function. So basically this is a way of showing a number of graphs to undertake analysis within the software itself. So basically this would then show a graph of saying, so actually for all my legs, if I change my network flow from 85 to 115%, so take 15% of my flow off or through the roundabout, this is a very quick way of showing which arm is likely to fail first. This is against BC. You could do the same with capacity. Basically using the XY graph, you can choose virtually any input and display a graph against any output. So this is a very quick and easy way of doing some analysis of a junction design or of seeing what the differences in flow might be without having to go through the process of entering lots of new data into the software. And like anything else, these graphs can be copied and pasted straight into individual reports. There is one of the outputs from the analyzer mode is the optimizer screen. So this allows you, so basically this is where you can attempt to find values of selected input variables that cause the values of selected output variables to meet user-defined targets. So basically you can say that I want my VC and all arms to be less than 0.85. So basically then you will enter which geometries you want to change and a range of values that they can use, and then it will then try and optimize those geometric parameters to try and aim or to try and get your identified output. So this is a way of potentially using the software to help in the design process, and obviously this will hopefully, once you've determined which of those geometric parameters you need to change and by how much, you can then choose to store that within the software, so that will then become part of your new design for that roundabout. So with the do calibration, so there's never been an attempt in the UK to drive a national or regional correction. It's always been a site-specific. Obviously, there is the application of intersect corrections, which, of course, like I said, is an adjustment made based on observed capacity. So this alters the position of your maximum capacity of intercept. So obviously this will then add or take away capacity from each leg in question. And obviously once your capacity is correct, then there's a very good chance that your predicted queues and delays are going to be representative as well. Excuse me. It may be possible to derive regional and national factors based on an average of many sites. We, at the moment, don't have access as a organisation to large amounts of site data from the US. Is something that we hope to rectify and something to investigate further. But at the moment, it's not something, unfortunately, that we have access to. So capacity adjustments can be made on different individual legs of intersections. These can be based on observations. You can apply a percentage capacity adjustment in addition. So basically, this can be a way of taking into account basically adding or taking away a percentage of capacity. So no matter how much the complex intersection may be, you can make an adjustment based on the capacity value.
And James, this is Lisa. You have about 4 minutes to
Cool,
wrap
okay.
up.
Sorry about that. Thank you. So one of the new features that was put into junctions was the entry lane simulation mode. So basically, at its core, Arclay uses the empirical models that relate to entry flow of a roundabout to the circulation flow past an arm. So one of the most important factors of that is entry width. And it was found that capacity increases continuously as entry width increases. And obviously this was found to be a better indicator overall, rather than the discrete number of lanes at the entry. There is an assumption that the entry width is available to all vehicles for most of the time. If there is a situation, for instance, where you have unbalanced flows, or if you have a small flare lane that's becoming blocked, then the core Arclay model may underestimate or overestimate capacity for that, and then it may well be a case of that your results are better than maybe expected. So we developed an entry lane simulation mode to model these on a lane-by-lane basis. So this is a way of providing the users to, say, model each roundabout design on a lane-by-lane basis as opposed to full entry width. So this is one of the new features. Obviously, you can then, this can even be used if you want to change lane assignment. So it's one of the new features, relatively simple. Once you've set up your core Arclay features and geometries, it's relatively simple to set up the lane simulation mode, and obviously then you can do a comparison between the core and the lane simulation mode. So this is some of the outputs of the simulation mode. So basically it will model each vehicle individually as it passes through, and it will then show those that are queuing on each leg and turn, and obviously it will then look at percentile queues and provide shaded percentile queues of which lanes that have the most usage and which are suffering from entry starvation. Obviously, it is possible as well to link junctions together, so any types of roundabout can be linked together. You can have a systems of 3 or 4 in a row, and obviously it will then model the interaction between the two. So any blocking back that occurs will then be transferred to the upstream roundabout, and then obviously the queues and delays will be passed between roundabout to roundabout. So I think this is probably hopefully the final slide. So this is just some of the other more features within the software. So it's really easy to set up bypass and filter lanes. If you have a short flare on an exit, then you can set up an exit restriction, or say where it merges from 2 to 1 an exit, so you can try and apply an exit restriction. It has the ability to apply national or regional calibration values if they're available. The ability to personalize window layouts to suit user needs. So if you can store different window layouts or features within the system, save that to file, and then every time you want to set up a new file, those windows are always there for you to access. There is now an audit trail which basically makes a track of every single change that's made to the system, to the model as you go through, so you can go back and check. Also, you can copy and paste, or even now read demand data from Excel, so there's a link between the two systems now. And we also have a link to Autodesk junctions, which basically, as you build a roundabout in CAD, automatically links to junctions or to Arclay and updates the results as well. We also have the ability to model the geometric delay, taking into account the fact that if you're introducing a network of roundabouts onto a corridor, it will then predict the geometric delay of each roundabout, so you can see how much delay you're introducing to that corridor just by the simple fact of the roundabout being there as a feature. And then you also have the ability to protect safety. It's only based on UK research at the moment, but we are looking to try and address that and increase the safety glitching to cover alternative states and methodologies. I'm not quite sure how I'm doing for time. I think that's probably just about it.
Yes, we are. We're ready to begin the Q&A, but first, I do want to administer a quick poll question. We're curious to learn how many people we have watching the webinar from your computer, so please use your mouse to best select what your room looks like. And I just want to thank James for today's presentation. Thanks, Mark. We're going to be transitioning to the Q&A in just a few moments. It looks like we have more than 60% of our audience members voting on this question. So continue to use your mouse and click on the button that best describes what your room looks like. And it looks like, Brian, we have received several questions coming in from the audience. So why don't I keep this poll question open for a few more moments as people are selecting their responses, and then you can start reading the questions that people are typing in.
Thank you, Lisa. Yeah, I'm going to start with a question here, and should I go another 30 seconds here as people fill the poll out?
Sure, go ahead.
Okay. So this first question, I'm going to have Mark answer the first. It's a question I'll pose to both Mark and James. And as I keep track of it on the screen here, let me go back to, it's a question that was posed about Q predictions. And let me get it in front of me here real quick. Sorry, it bounced around as if somebody added a question that moved my screen. Mark, can Rodel model Q delays? For example, if there's an intersection that is not working properly that's downstream of an exit and it is backing the traffic into the roundabout, can this be modeled in Rodel? Or does the software only model ideal conditions? And I'm going to pose the same question to James as well on Arcady. But Mark, go ahead.
And just a reminder, Mark, to please unmute yourself. We are currently not able to hear you.
Thank you. Give me the second shot at the answer now. Hopefully you can hear me now.
We can.
Queuing from a downstream intersection, if it was a signal, if it was a roundabout, Rodel is not a simulation program. It doesn't link intersections together. So in that respect, no, it wouldn't be able to account for queuing back into the roundabout that you were analyzing. But it has many capabilities for linking roundabouts. You can, for example, export the flows from an exit and feed those directly into a roundabout downstream to model the effects of the exit profile from an upstream roundabout to that downstream roundabout. But if you have different intersection types, then you would need a different tool to analyze that as a system.
Okay. Thank you, Mark. James, did you want me to repeat that question? And I wonder if the question or the answer is a tad different in the Arcady program and how you might. Should I go ahead and repeat that, or did you get a chance to?
It should be okay. Thank you.
Okay.
It's similar, kind of similar response to Mark. If it's two linked roundabouts together, there is an option. If it's two roundabouts linked together, then there is an option within the software to basically set a storage level in between the two roundabouts. And once that storage level is full of queues, then it will basically then stop the upstream arms from feeding into that roundabout. So it will model the interaction between two roundabouts. And if that storage space is full, then it will basically back up to the next roundabout, and then you'll start getting queues developed on the preceding arms. If it's not a roundabout, if it's a signalized junction or a priority junction, two-way or four-way stop, you can't link those junction types together at the moment. What you may be able to do is there is an ability to apply an exit restriction. So if there's a maximum flow or minimum flow that's allowed to go, that's able to fit through an exit, you can apply the exit restriction, and it will have a similar effect of the link of the roundabout. So basically, only a maximum flow would be able to exit on that arm or that leg, sorry. And basically, if that maximum minimum capacity is met, then again the queues would then, demand would be held upstream and within the other legs of the roundabout until they can flow through that exit.
Okay.
Brian, if I could just follow up real briefly, if that's okay.
Go ahead.
If there was a downstream signal serving the entry to the roundabout, you can, not explicitly like in a microsimulation program, but you can account for the platooning arrival of that signal as a concentrated flow with various testing methods within Rodel.
Okay. Thank you, Mark, and thank you, James. The next question will be the same thing. I'll ask James the question first, and then I'll have Mark respond on the Rodel side. When you guys look at many roundabouts and analyzing them, designing them through these two programs, do you see a difference between the U.S. definition of many roundabouts, where some of them may be a mountable central island and contain the driving path with curbing, or more of the UK style of a mini roundabout that would allow just paint out there? James, does that question make sense, and is there anything that Arcady would look at differently with those types of so-called mini roundabouts between the two countries?
Yes, there is. I mean, we have developed, say in the 90s, we developed specifically a mini roundabout model which looks at the design, the UK mini roundabout. So basically it has a completely different set of geometric parameters that you need to enter into the software when doing a mini roundabout. For it to be considered a mini roundabout, it does have to have a traversable central dome. So if it's got a raised central island, even if it's still very small, then basically if it's got a raised central island, you may be better off using the full normal roundabout model. Basically in the UK, the mini roundabout has to have a traversable central island, 4 meters or less. So obviously if your central island is raised and greater than 4 meters, then you're kind of outside the bounds of what are considered a mini roundabout in the UK, and in that instance we'd recommend you use the normal roundabout model. Okay,
thank you. Mark, any thoughts there on how Rodel handles that dynamic?
Rodel, you used it, and it doesn't have a specific mini roundabout mode. Minis have a upper limit on operations typically. So what we've been doing with minis is we put in the geometry for the minis, which is a very small geometry, and Rodel, like Arcady, would account for that smaller geometrics. We also then put in a slight capacity reduction on top of that to be somewhat conservative in terms of the testing of the operations of that mini. So within a mini, you can have variation in geometry as you're describing, from kind of a mountable domed UK style versus some of the terminology that we're getting in the U.S. is sort of, there's terms such as a MIDI, which is more perhaps a larger mini, or a smaller single lane, and so you account for the geometry, and the 6 geometric inputs will reduce that capacity, and then if you do some testing, you can accurately reflect the operations of the various sizes and shapes that you can get within the mini area.
No, that's great. So this next question for both of the presenters, I think that there's a lot of questions that certainly cross over. Same thing, Rodel and Arcady with oval or elliptical shaped roundabouts. Mark, you may have hit on it, but if you wanted to maybe give us a 30-second thing about Rodel, and then James, I'll ask the same question of you.
Yeah. So yeah, with the 6 geometric inputs for each leg, you can specifically model the geometry of each leg of a roundabout. So with respect to various shapes of circles, of roundabouts rather, you can account for the geometric conditions of those shapes.
Okay. James?
Yeah, it's very similar. So we use the same geometric parameters. So like Mark said, those 6 parameters will account for any different shape of roundabout, really. The only difference is when you have a standard circular roundabout, your square circular diameter will generally be the same. Obviously, if you have an oval roundabout, then your ICD value will vary for each armature.
No, I appreciate both your answers. There's a bit of redundancy with that question, but I think it's important for the audience to recognize that non-circular shapes are a reality, and in many cases with constraints, these programs can be used effectively to model and design non-circular shapes. Thank you. This question would go to James, this next one. James, it was specific to Arcady. Can you express the output file that would show the 95% Q in it instead of, and I don't know this term, the PEC in Arcady?
Yes, you can basically get it to predict the 95th percentile Q. There's an option within the system to do Q variations, so it will predict the 5, 50th, 90th, and 95th percentile Qs for each leg. So yeah, it's basically it's just a drop-down menu, select it, and it will do the Q variations and predict those end results as well.
Okay, thank you. A lot of questions came in after James finished up for both of you, but I'm looking through some of them and trying to prioritize them. Turbo roundabouts were mentioned but not shown. Mark, any comments about turbo roundabouts and any Rodel specialty piece to that, or whether or not there's some judgment involved there?
Yeah, turbos again is a term that essentially, from what I can, as I'm, different people are using it for slightly different things, but is essentially a roundabout that includes spiral applications. Some of the turbos have raised islands between lanes on the circular roadway, while others are just paint, and the word is being used interchangeably for each of those. We've been using Rodel to model these types of roundabouts, whether they're turbos, spirals, hybrids. In essence, it's modeling the geometry, and so in accounting for the entry angle and the various geometrics. So for U.S. application of what we're seeing for turbos, we've been using it on those for the laneage. Perhaps when you get into some of the more specific type of turbos we're seeing in the Netherlands, for example, there may be some differences, but we feel confident in the fact that if you have a very perpendicular entry with tight radiuses and smaller entry widths, that Rodel can account in large respect for those operational influences that geometry will have.
Okay. James, any thought on turbos and their applicability to Arcady, or Arcady's applicability to turbos?
Again, it's kind of a similar answer. I mean, obviously, in many ways, Arcady, although it doesn't really model the circulatory carriageway, there's a basic assumption that you have enough lanes within the circulatory carriageway to cope with all the lanes entering it. So basically, there should be no inhibition within the circulatory carriageway. So the fact that it's just a measurement of the entry width or the entry approach. So in that case, it should model a turbo roundabout without any difficulties. We just introduced a couple in the UK, our first few turbos as well. So it's more than capable of, in theory, modelling that type of roundabout.
Okay, thank you. A couple questions came in about the pedestrian crosswalk piece and whether or not that can be modeled. And I will ask Mark first. Can you model pedestrian volumes, crosswalk location pieces?
Yeah, Rodel includes the capacity reduction factors developed for the U.S. And so that's it's an input that you input that factor based on the volumes of PEDs across an entry or exit.
Okay, James.
Yeah, we have a pedestrian model in the system. Basically, at the moment it's based on the UK zebra crossing and signalised crossings. So basically, you specify whether it's non-signalised crosswork or signalised. If it's unsignalised, then basically you enter how many PCUs or PCEs can fit between the roundabout entry and the crossing, the length of the crossing, and then basically it will then, depending on the amount of flow, pedestrian flow going through the crossing, it will inhibit the capacity, so that you will see a capacity reduction based on the number of pedestrians, the length of the crossing, and how much space is in between the crossing and the yield line.
Maybe a selfish question from the moderator. Do you have a number that starts to really impact an entry or an exit flow that seems to be a threshold number or a range?
It depends a bit. I mean, there isn't one.
Okay, I just wanted to pose that for the audience's benefit as well. We don't want to predict numbers that, yeah.
Yeah, I mean, obviously, it all depends. There's a number of variations. If the further away from the yield line you get, obviously, the less effect it has. But obviously, the closer you get and the higher the volume, then the greater impact it's going to have. Generally speaking, for the core model, it will only do model the capacity effect on the approach and exit to the next proceeding arm. But if you use the entry lane simulation within Arcady, it will then model the effect on entering capacity to every single arm. So if you have a very dominant crossing, then it will potentially lock up the whole roundabout. So
makes sense.
Yeah.
What I really like about both of these programs, from my limited experience with them, is that there's geometric pieces that are pretty important in the input. And here's another question that requires probably a little bit of judgment, but I'd like to hear both of your explanations or your thinking process with them. Is there any variation of capacity that results from using a higher truck apron, maybe a 4-inch truck apron versus a 2-inch truck apron? I'm guessing I don't know the answer, but I'm going to pose those questions. Mark, why don't you go ahead and take that one on first? And do you see a geometric piece like that ever being able to be modeled?
The answer is no and no.
Yeah, it's good. I think some people hear about the geometric pieces of Rodel and Arcady and might think that this could fit in there, and it's a good question to pose.
Yeah, I mean, the apron curbing is what you're referring to, right?
Correct. The height of the apron curbing.
Yeah, that's. I mean, yeah, that's a not included in the geometric parameters.
Not one of the 6 main features. Okay. And James, I imagine I could ask that question, but I think I'll hear the same answer. Would that be fair enough?
Pretty much, yeah. I mean, like I said before, we don't really model the circulatory carriageway. It's just assume the space is there to cope with the vehicle entering it. So it's not something that's considered at the moment to have an impact on capacity.
Okay. Both of you mentioned calibration in your presentations, and I wondered if certain states and municipalities have started their own calibration efforts with a number of models, and I assume with these as well. Any words of wisdom there? Mark, I'll start with you on calibration. Actually, James, I'd like you to start with this one. You talked a little bit about calibration, and I'm posing the question, do you do a lot of calibration for people, or is there people that ask that question a lot, and how do you help them?
So generally speaking, I said in the presentation, calibration, especially say what we've done in the UK, mainly it's on a site-by-site basis only. There's no national or regional value that we've ever applied to a model. I mean, the way that you generally calibrate a model is you observe a roundabout in queuing conditions, and obviously you basically then do a number of counts of vehicles passing the yield line and then in the circulatory carriageway. And then so basically you're observing actual capacity, and then you make that calibration.
Okay. That
calibration change based on your observed capacity. I know there's always been a talk of whether the UK is applicable to other parts of the regional other types of the world. I mean, generally speaking, it's the parameters are always going to have an impact on capacity, probably no matter where you're building a roundabout. Those changing capacity of geometry parameters are unlikely to have effects that are going to vary on a wide basis. So, and we're obviously aware that a number of people are obviously using Arcady and the Kimber methodology in the States, and it's quite well known and other areas in the world as well. So we're fairly confident that the actual capacity equations and model itself is fairly robust. So.
Okay. Mark, any additional thoughts from the experience you have?
Yeah, well, within the HCM model, folks are using different gaps within the HCM model for different states, and that's easily input into Rodel, and you can then set that as a calibrated setting. With respect to the UK model, the empirical model, we're reviewing the US data compared to Rodel's predictions, and we're finding strong correlation with the US data, particularly the saturated data that's coming out more recently here in 2012. That's, as I mentioned in my presentation, will be used to provide an update to the HCM. And so while the ability to calibrate is quite easy within Rodel, whether it's the HCM model or the empirical model, with respect to increasing the y-intercept, if you want to adjust the slope to better fit data, we're very cautious in recommending that currently, in the sense that, again, we're finding very strong correlation with that data. You know, it's because of the geometric influence, it's performing and predicting for these various sizes and shapes of roundabouts very well. And so, I mean, at some point, if data is available and you know, someone could set out to conduct that and understand, you know, what type of calibration may be necessary. But we like the ability to model these different sizes and shapes of roundabouts and have a program that accounts for those different sizes and shapes, because I'm of the thought that has a stronger influence and some of the other design components than specific differing driver behavior from region to region. You know, we don't use different calibration necessarily for signals across the country. Driver behavior is assumed to be similar. We understand there is variation, you know, from rural to urban and those sorts of things, and some variation region to region. So obviously there could be some calibration that could occur. But we're using it as it is, out of the box, as it were. We're then testing for variability within driver types and making sure our designs are robust, understanding that you do get different driver types within an area that can affect your performance. And then making adjustments to make a design more robust to account, for example, for a driver that is not as assertive as another driver.
Appreciate that. James, did I pose that same question to you, or did you answer that? I apologize. I was thinking about the next question.
No, I think I went first on that one.
Okay, thank you. I appreciate that. It's been a long morning. Obviously, for some of you, it's a late afternoon. But I have one more question for both of you that I wanted to talk a little bit about. And James, I'll lead with you, and then maybe it puts you at a little bit of a disadvantage. I'm sitting across the Atlantic. From a cultural standpoint, in this country, a number of practitioners separate out the analysis and the design functions. And I wanted to hear maybe some insights you might have to how that might differ in the UK, parts of Europe, and whether or not you do both of these with this program, the design and the analysis, or whether or not you see municipalities in the UK separate out those functions. Any thoughts on how your program gets used that way?
It's, in many cases, it will always depend on how individual authorities are set up. I mean, me personally, I'm a traffic engineer, senior traffic engineer, so I do both components. I do design and analysis, and obviously it goes hand in hand. It goes hand in hand. It's not a fully separate process, and from my experience and knowledge of users, it's something that should be done as you go through the design process, as opposed to chopping and changing. But we're aware that some organisations always do it differently. I mean, like I said in the presentation, that we have a link to the CAD software package. So basically, as you're designing your roundabout within that CAD package, it will automatically transfer the flows and geometries between the two. And as you make changes to the design within the CAD software, then your capacity equations will automatically update. So there's probably hopefully a trend towards more a joined up process between design and analysis. This to say, something that I do as an ongoing process throughout the design, rather than seeing it as a completely separate entity, if that makes sense.
No, well stated. Mark, some thoughts on your experiences with the cultural pieces that apply and the software that you use. Yeah.
Real briefly, you can use the program for planning purposes and analysis purposes, and then you can also use the program to do preliminary and final design. As James mentioned, I mean, when you get into constrained situations and feasibility, that geometry and its feasibility are closely linked together, and that's when you're into needing to have a good understanding of the analysis side and the design side, and that can be true in many situations. But then there are situations where it's not as important, and you can do that. You can have the separate analysis and the design. But when you get to design, you do need to bring along that analysis, I guess, would be a caveat to that, as opposed to completely separate.
It sounds like both of you described it as a bit of a circular process where there's a good check and balance where you come back to the analysis to double check. And clearly the program does some of that, but you keep checking back through the numbers and the parameters that you have from a design standpoint to make sure you haven't missed anything or you tweak it.
That would be accurate, yes.
Yeah. Okay. A question here. I'm getting back to the technical side. When I was looking at the time, we have about 4 minutes, and I had just a quick thing that these are always good questions because I don't know how many of the audience might need this information. But in terms of truck percentages, James, how does Arkady take into account truck percentages? Is there a short and quick answer to that?
Yeah, basically you just enter the percentage for each leg for each movement.
Okay, so let me ask you this: Does it go ahead and do a per car equivalent? Is there a?
You set up a heavy vehicle value. So you say one heavy vehicle is the equivalent of 2 standard cars. So basically it's 2 PCE per obviously HUV, and then you just enter that percentage. Obviously, if you might have slightly bigger rigs in the US than what we have in the UK, so you may want to maybe increase that to 2.2, 2.5, and then basically once you've done that, all the subsequent calculations are undertaken internally.
Okay, thank you for that. Yeah, detailed explanation. Mark, any differences that Rodel would take that?
No, it's identical.
Identical. Okay, just wanted to kind of get that on the plate for the audience to recognize that the thought process between the two programs is the same. I didn't have any additional questions, although there are questions, obviously, but I think some of them have been answered by the presenters themselves. This would be another cultural question, maybe to close it out, and we have 3 minutes. Is when a designer is working on a roundabout design, do they run more than one soft program? Do they? And this is obviously a planted question to you guys. Would you ever use another program to take a look at things for a client's request, that type of thing? It was specific to higher capacity roundabouts too.
Sorry.
Go ahead, James.
Let's say we never have.
Okay.
Basically, we've never been asked to, and we wouldn't anticipate doing so.
I probably won't get a passing grade on this question. It was something that came in, and I thought I would ask it. We
Brian,
go through this as a practitioner, Mark, and so in the
U.S. we have different agencies that are more comfortable with different programs, and so it's quite common to be using various programs on the same project, and so it's quite common to have different tools being utilized, and frequently we're using the deterministic tools, and then also using simulation tools as well to account for network issues as well. And so in the U.S. there's a quite a range of tools being utilized.
Yeah, as a practitioner, I will just confess to the audience that we certainly look at a number of different tools because the world's been gracious, and the United States is a collection of a lot of those tools for this roundabout thing that started up the last couple of decades. So with that, I'm going to I wanted to put in one more plug that this was the second in a series of the analysis tools for the capacity and efficient flow for roundabout design. We will have a third one in July. And I want to go ahead and remind the audience that that's July 14th. And much like you signed up for this one, we would love to have you attend it. This is mostly going to be simulation programs in those tools and how they apply to roundabout design. I wanted to thank James as well as Mark. Thank you both for your presentations and time today. I want to thank TRB for hosting this and facilitating it so well. We need all the help we can get sometimes when we're, as a committee, trying to put on these webinars. So much thanks to many of the people at TRB. With that, I can end the program, and thank you so much, folks, for attending today, and we hope to see you on July 14th.
Actually, just one more thing. I want to thank the audience for joining us today. And when you sign out of this session, we encourage you to take a brief evaluation regarding your experience. We use these evaluations to improve our webinar program, so your feedback is greatly appreciated. And yes, thank you again, Mark, James, and Brian, for the presentations and discussion. And have a great afternoon. We hope to see you for the third webinar on July 14th. Take care.
Thank you, Pete. Thank you.